everyone, this is Mr. Stelzer, and welcome to the YouTube channel. So what I'm going to do for you tonight is I'm just going to go through and I'm going to work through the exam review for AP Chemistry in their Unit 1 and 2 exam. So the idea behind this is I'm going to work through the exam so you can see me do it. I'm going to try my best to talk through what I'm thinking. So not only for the reviews will you have the actual answer key, but you'll also have this video in order to see me actually do these problems as well for your own studying. So without further ado, let's actually get into the review. We're going to do one video for multiple choice, one video for FRQ. So this will be the multiple choice one. Let's start off with the multiple choice. What color are we feeling today? I'm thinking like a green. So 14 questions. Remember, you get 14 questions in 21 minutes. That is a minute and a half per question. Let me down the size of this. It is too big. Maybe like that. That's better. All right, let's get into it. In which of the following compounds is the mass ratio of chromium to oxygen closest to 1.62 to 1? So we had a question like this in the homework actually. So we have a compound made of chromium and oxygen. We're trying to get a formula, and formulas are mole ratios. We have a mass ratio. This is a mass ratio. We need to get that to a mole ratio. So the first thing I'm going to do is, if my mass ratio is 1.62 to 1, that means I don't like how I'm moving that, 1.62 grams of chromium for every 1.00 gram of oxygen. Because if my mass ratio is 1.62 to 1, then my mass for every 1.62 grams of chromium, I would have 1 gram of oxygen. Let's dimensional analysis this. I have to go to the periodic table to get these molar masses. Let's try and remember chromium and oxygen. Chromium is 52 grams per mole. Oxygen is 16. Should be easy to remember. Oops, this one. Back to full screen. So chromium, 52 grams per 1 mole. Oxygen is 16 grams per 1 mole. Let me get my calculator out. 1.62 divided by 52 is, was a bad equal sign, 0.0311. 1 divided by 16 is 0.0625. And that is the mole ratio. So from here, I would be able to see that, okay, I have twice as much oxygen as I do chromium. But remember, to get it to whole numbers, one thing we can do is just divide by the smallest. So I did not mean to do that. Let's divide both of these. I gotta fix this. This is annoying. Maybe just zooming out will help. Let's divide both of these by 0.0311. And then we get 1 chromium for 2 oxygens. It's CrO2, which is B. All right, let's continue on. The mass spectrum of an average sample of a pure element is shown in the figure above. Which of the following is the identity of the element? So the molar mass on the periodic table is an average atomic mass of all the isotopes. So what we're doing is we're going to go to the periodic table and see what molar mass on the periodic table matches with this mass spectroscopy data. So as you can see, we're going to be in between 90 and 94, but I think we're going to be way closer to 90 than we are to 94 because we're way higher weighted 90. I would predict we're going to be somewhere around there, like 91. So let's go back to the periodic table and let's find where we can see something around 91. And I see one. It's zirconium right here. Zirconium is 91.22. 88.9 is outside the range. 92.9 is close to 93, that's not what we were looking for. Zirconium is the only one that makes sense. And zirconium is on there, so it's zirconium. Which of the following has bonds arranged in order of decreasing polarity? So we're ranking from most polar to least polar. For bonds, polarity is based off of difference in electronegativity. So we're going with the highest difference to the lowest difference. And right away, I see A stands out here because FF is nonpolar, and our lowest polarity should be the last. HF, NF, FF makes sense. HF is the furthest away. NF, N and F are both two of the big three, and then FF is the same, so that's nonpolar. All right, we have the photoelectron spectra data above. This is PES, and it's showing the energy required to remove a 1s electron from nitrogen and 1s from oxygen. So that's kind of important to note. Actually, not kind of important. That's important to note. This is not the outer layer of both of these things. This is the innermost layer. This is the 1s of nitrogen and the 1s of oxygen. Which of the following statements best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? So we're asked, why is nitrogen's peak further to the right than oxygen's 1s peak? So again, these are not the outer peaks, these are the inner peaks. Why is oxygen have a higher binding energy that looks around 550? 550. Nitrogen's looks around 400. Why does oxygen have a higher ionization energy on its innermost orbital? Well, oxygen has one more proton. That's why. Oxygen has an extra proton, so it holds onto the inner level a little bit higher due to Coulomb's law. Nitrogen atoms have half-filled p subshells. That's not the reason. There are more electron-electron repulsions in oxygen atoms. That's not what we said. Electrons in the p subshell of oxygen atoms provide more shielding than electrons in the p subshell of nitrogen atoms. They're just trying to throw chemistry terms on you and see if one sticks. The answer is nitrogen atoms have a smaller nuclear charge. Nuclear charge, if you recall, is that Coulombic attraction between the nucleus and the electrons. So it is the nuclear charge option, D. I should be checking my work as I go. Let me see. It is D. All right, which of the following is the ground state electron which of the following ground state electron configurations represents the atom that has the lowest first ionization energy? So first ionization energy is the energy to remove the outermost electron. So we're looking at this electron, this electron, this electron, and this electron. The answer here is D. Remember, ionization energy dramatically decreases with size. So it's Coulomb's law. The further away from the nucleus an electron is, the easier it is going to be to remove away. So the one that's removing from the 3 here is going to be way easier to remove than removing something from the 2 or something from the 1, and none of them are removing from the 1. We can also, by the way, we can just classify these as their elements. 1s2, 2s1 is, let's see if I can do this without going to the periodic table. Hydrogen and helium, this is lithium. This is carbon, this is neon, and this would be sodium. Sodium has the lowest first ionization energy because the trend goes up and to the right, and sodium is like right here, lithium is like here, and then carbon and neon like are over there. So sodium has the lowest. 23.6 gram sample of a compound contains 12 grams of carbon, 3 grams of hydrogen, and 8 grams of oxygen. Which of the following is the empirical formula of the compound? So once again, we need to get an empirical formula, and we're given information about mass. So we need to get to moles first. So let's get to moles. We have 12 grams of carbon, 3 grams of hydrogen, 8 grams of oxygen. And this multiple choice question picked these numbers for a reason. That's to make your life easy. Carbon is 12 grams per 1 mole. I know it says like 12.01, but it's a multiple choice question. We can simplify. Hydrogen is 1 gram per 1 mole. Oxygen is 16 grams per 1 mole. So we end up with 1, 3, and 0.5. To get them all to whole numbers, we can divide by 0.5, which is the same as multiplying by 2. And we get 2, 6, and 1. So 1 to 6 to 2. And that is the empirical formula. So 2 carbons, 6 hydrogens, 1 oxygen. It's that one. It is B. All right. The table above shows the melting point for magnesium oxide and sodium fluoride. Which of the following best helps explain why the melting point of MgO is much higher than that of NaF? So we can see that in the graph. They didn't need to point out that fact for it. They can have said which of the following accounts for the chart. Look at how the melting point of MgO is so much higher than NaF. Why is that? Well, let's go to the periodic table again. We go back to our periodic table. So magnesium and oxygen and sodium and, was it sodium fluoride? So we have magnesium, oxygen, and we have sodium fluoride. There's not a huge size difference here because magnesium is close to sodium and oxygen is close to fluorine. So what's actually going to be determining the lattice energy, how strong it is, and that's the melting point, is how strong the charges are. Magnesium forms +2s, oxygen forms -2s, fluorines form -1s, sodiums form +1s. So by the charge, the magnitude of these charges for magnesium and oxygen are higher than the magnitude for fluorine and sodium. And according to Coulomb's law, the higher the magnitude of the charges, the stronger that force of attraction is. So that's what we should be looking for here. Back to full screen. The mass of F ions is greater, has nothing to do with mass. The mass of Mg, 2+ ions, is greater, nothing to do with mass. The difference in electronegativity values between Mg and O is smaller than the difference between the values of Na and F. That sounds like polarity of bonds, which is not what we're doing here. D is the answer. The charges of magnesium and oxygen ions are greater than those of sodium and fluoride. Given the density of mercury at 0 degrees Celsius is about 14 grams per milliliter, which of the following is the closest to the volume of 1 mole of mercury liquid at this temperature? This little L is liquid. That's just the state. Mercury is a liquid at room temperature and at 0 degrees Celsius, which is why it was used in a whole bunch of thermometers, because it was one of the naturally occurring liquids that are elemental. This one was evil. This one, they struggled on this one last year. Okay, we're given a density. So first of all, temperature is a complete misdirection. We haven't done anything with temperature this year yet. Don't pay attention to the temperature. That's just there to distract you. We're focusing on this. Density is 14 grams per milliliter. And we want to know how many milliliters is 1 mole of mercury. Well, this is just doing some dimensional analysis. If we have 1 mole of mercury, go back to the periodic table, let's find out how many grams is in 1 mole of mercury. Mercury is down here, it's 200.59. I'm just going to say 200 since this is a multiple choice and it doesn't matter that we're exact because we're picking from a set list. So 1 mole of mercury, for every 1 mole of mercury, there is 200 grams. That comes from the molar mass. And then we can use this as a conversion factor for our dimensional analysis. There are 14 grams of mercury for every 1 milliliter of mercury. So moles cancels out, grams of mercury will also cancel out, and we're left with milliliters, which is what we want here. So let's do the 200 divided by the 14. 200 divided by 14. And that gives us 14.3. So 14 milliliters it is. I'm going to do check D, and the other one's D2. Good. Which of the following Lewis electron dot diagrams best represents a molecule that is most polar? So we're looking for most polar. Polarity is imbalance of electrons. So we're looking for which of these molecules has the greatest imbalance of electrons. So right away, I'm going to eliminate 2 of them. D and C are both nonpolar. This is trigonal planar, and since all of these are fluorines, there's no imbalance of like elements going on. That's a symmetrical shape with symmetrical elements, nonpolar. Same thing for this chlorine or this carbon disulfide. Also nonpolar based off its symmetry and the elements that make up the molecule. A and B are both going to be polar, not because they're asymmetrical in shape, but because they're asymmetrical in the elements that are on either side. So the question is, which one is more polar than the other one? Well, the one that's going to be the more polar one is the one that has like a greater difference in electrons. Bromine is has more electrons compared to chlorine. For that reason, the bromine fluorine molecule is more polar because there's a greater difference in electrons. Fluorine is a constant for both of these, and if we have to go to the core electrons in this case. Chlorine has X amount of core electrons. Bromine, has way more of core electrons, so we're going to have way more of a negative charge on that one. So the answer is B. A sample of solid labeled NaCl may be impure. Ooh, one of my favorites, a impurity question. A student analyzes the sample and determines that it contains 75% chlorine by mass. I kind of failed to underline that, 75% chlorine by mass. Pure NaCl contains 61% chlorine by mass. Okay, so they give us what the mass percent of chlorine is. They didn't, in sodium chloride. They didn't need to do that. We could have found that out. We could have easily found that out. We know how to do that, but they gave it to us. Which of the following statements is consistent with the data? So, our mass percent of chlorine, we have a sample. Let me draw a bowl. We have a sample, and in this sample is what we thought was pure NaCl. But when we took the mass percent of chlorine in the sample, we found that it was 75% chlorine. That's a problem because NaCl is only 61%. So what's happening? Something's in there contaminating it. Something is in there driving that percent mass of chlorine up. So what is it? First of all, it's not pure NaCl because the mass percents need to be matching if that's the case. It's also not NaI because NaI would be driving the percent mass of chlorine down. There is no chlorine in NaI, so if we add NaI, we're diluting the chlorine. It's either KCl or LiCl. And without even doing the math, I know it's going to be LiCl. Lithium is like 7 grams per mole. Chlorine is like 35 grams per mole. Lithium has a very high mass percent of chlorine. It's 35 to 7. Potassium is way more than that. Potassium is above 35. It's like 40 or something like that. So it's actually going to have less than a 50% mass of chlorine. The answer is lithium because lithium being in there would drive that mass percent out. And you can do the math and determine that for yourself, but it's multiple choice. Let's take shortcuts if we can. All right, 10 down, 4 more to go. Do I have those other 4? I do. They're right here. According to Vesper model, the progressive decrease in bond angles in the series of molecules CH4, NH3, and H2O is best accounted for by the... So what it's saying is, like, if we have methane here, CH4, this bond angle is 109.5. But if we have NH3, this bond angle is like 107. It's less than 109.5. Why is that? Is because there's a lone pair. And for bond angles, lone pairs take up more space than bonded atoms. So if that lone pair being there kind of pushes everything further away from it. So the answer is the lone pair. We just have to pick the one that's saying that. Increasing strength of bonds, increasing size of central atom, increasing electronegativity, increasing number of unshared pairs of electrons. Ding, ding, ding. That's a lone pair, just said weirdly. Decreasing repulsion between hydrogen atoms. Nope. The rest of those are just lingo. It's the one with about unshared electron pairs, which are lone pairs. Which of the following diagrams best illustrates how displacement in an ionic crystal results in cleavage and brittleness? Brittleness is the word I'm going to focus on there. Why are ionic compounds brittle? Is what this is asking. It's specifically talking about ionic crystals. So first off, let me zoom out a little bit. 2 of these are not ionic. This one is not ionic. This one is not ionic. That looks more like an electron C to me. And this one is not ionic. That looks like something that you would see in biology class. Not my class. Go ask Miss Glover what that is. I don't know what that is. We don't look at things like that. Long carbon chain of something. A and B both look like ionic compounds. Why are ionic compounds brittle? When we hit an ionic compound with a force, when we hit salt with a force, it breaks into smaller pieces of salt. What we're not doing is we're not changing the chemical identity of ions in there. We're not taking ions and combining them into super ions. What we're doing is we're shifting the lattice, and as soon as we shift the lattice a little bit, all of a sudden we have negatives next to negatives and positives next to positives, and like charges, just like how opposite charges attract, like charges repel, and then these two will repel because they're next to like charges. A is the answer. All right, last two. We are very close. Let me go back out. The table provides some information about two types of steel, both of which are alloys of iron and carbon. Which of the following best helps explain why the high carbon steel is more rigid than the low carbon steel? So, let's see. Let's read through the things. Elemental carbon is harder than elemental iron. The additional carbon atoms in the alloy make the high carbon steel less dense. The additional carbon alloys within the alloy increase the thermal conductivity of the high carbon steel. The additional carbon atoms within the alloy make it more difficult for the iron atoms to slide past one another. So, metals are malleable, which means if you hit them with a hammer, they bend. This question is asking, when we add carbon in there, does it bend less? So if we kind of look at the structure, if we imagine a metallic lattice with irons, when we hit it, it's going to bend. There's before and after. When we add carbons in there too, this is going to be an interstitial alloy. It's going to bend less. To me, that seems like those carbon atoms are kind of restricting the motion of the iron atoms. Now, that's not something we strictly went over in class, but AP Chem will do this. They will throw you things that you have not seen before and expect you to kind of draw upon what you do know to make an inference, to make a judgment. So which one of these is saying that? It's not that elemental carbon is harder than elemental iron. It's not that additional carbon atoms within the alloy make the high carbon steel less dense. It actually makes it more dense. We're adding more thing per square meter. The additional carbon atoms within the alloy increase thermal conductivity. That means we're not talking about conductivity, we're talking about malleability. The answer is D. The additional carbon atoms within the alloy make it more difficult for the iron atoms to slide past one another. Kind of a tough one. Alright, which of the following best accounts for the decrease in the first ionization energy of the alkaline earth metals going down in the group? Alright, that was a mouthful. Decrease in first ionization energy of alkaline earth metals going down. So, go back to the periodic table. Here are alkaline earth metals. Why does ionization increase and ionization energy decrease as we go down? Well, as we go down, we get bigger. That's it. We have bigger atoms, and we know, according to Coulomb's law, that the further away an electron is, the easier it is to remove. And ionization energy is energy to remove an electron, so of course it's going to decrease as we get bigger. It's going to become way easier to remove as we get bigger. So let's just go back and find which one says that. The number of protons in the nucleus increases. That is a thing, but that would cause an increase in ionization energy. The number of protons in the nucleus increases. Again, that would cause an increase in ionization energy. It's not that. The number of electron shells increases, resulting in a greater average distance between the nucleus and the electrons. That is the answer. That's what we're looking for. D says the number of electron shells increases, resulting in less shielding between the nucleus and the electron being removed. That's not shielding, there is no such thing as shielding between nucleuses and electrons. They don't shield each other, they're attracted to each other because they're oppositely charged. There's electron shielding between electrons and other electrons, but this is, again, they're trying to throw lingo at you. You kind of have to filter through all that and find out what you need to know that to do the question. All right, that concludes the multiple choice section. I guess I'll see you guys in the FRQ video. So I'll end this video and I'll get that one started. All right.